distinguish now is this notation. I'm going to use it to denote equilibrium averages. So this means taken as usual with the partition function. You put the observable, which is this dot here, within the partition sum, and then you normalize. So this is the usual equilibrium measurement. And yesterday I didn't use this subindex ek here, but I think that it will be clearer if I use it. So I'm going to introduce it now. Yesterday I used this one to denote dynamic averages taken over noise realizations. So if I think in terms of an evolution dictated by a Langevin equation, this means averages over different realizations of the noise taken with the probability distribution that I will attribute to the noise. And I didn't introduce yesterday, but I want to introduce it now a little bit because with Anatoly's talk I thought I should have done it. An average over initial conditions. So why didn't I introduce all these averages yesterday? Because in the back of my mind, and the back of all our mind, we always have the idea that typical initial conditions will give you the same kind of evolution than the one that you get when you do averages over different initial conditions or over different runs of the noise. So in our field, at least when one thinks about these coarsening problems, it's not absolutely necessary to take these averages, because if you take a sufficiently large sample and you let it evolve from a typical initial condition with a typical realization of the noise, then you will get the same for all of these. So this is why, well, okay, we didn't think about distinguishing these yesterday. But okay, to make things more proper and more precise, it is necessary to introduce these notations. So this is why I'm doing it now. So let's say that I'm going to call psi the noise, but this will come a little bit later today in the talk. I don't really have ergodicity in the equilibrium sense, because my dynamics is taking place out of equilibrium, and it has nothing to do with ergodicity in the way that one studies it in graduate courses. Still, I have some, between inverted commas, some kind of dynamic ergodicity in the sense that, you know, if you don't take a very peculiar initial condition, very special one, like the one with all the molecules in the corner of the room, let's say, then everything will behave in the same way. So think about a random walk, the Brownian motion that you know, we all heard sometime. There, it doesn't really matter where you put your particle initially. When you take your Brownian particle and you put it in the fluid, it doesn't really matter if you put it, you know, far away from the center. Or after a short transient, all of these motions will, on average, statistically, do the same. Statistically, this is what I mean by the not special influence of the initial condition or of the special noise. So in the Brownian problem would be the special experiment that you do. I mean, you put the particle once in a position, you take it out, you put it again in the same position, let's say, so that you don't have fluctuations induced by the initial condition. But of course you will have induced by the noise, because collisions that the Brownian particle will feel will be different in the second experiment. Still, statistically, the behavior of the particle will be the same. So this is what I mean by little influence of the initial condition and noise. But still, okay, let's keep these notations. And I'm going to go back to what I started discussing yesterday, which was the issue of separation of timescales and scaling. Better said, dynamic scaling. Okay, so yesterday I started discussing the problem in which you have a control parameter, let me call it T over J. You start from a very high temperature initial condition, so in the disordered phase, and you quench the system to the critical point. I started discussing the scaling that one finds and the separation of timescales that one finds when one quenches to the critical point, and I was thinking about a second order phase transition. Separating the disordered phase from an ordered phase with an order parameter, and the example that I was talking about was the example of magnetic systems for example, the Ising model, say in 2 or 3 dimensions. So, just recalling what I said, I talked about the equilibrium correlation function in space, and this I defined in the usual way. The correlation between two spins at a distance r within the sample. And I said that at the critical point in equilibrium, so here let me write ek to stress the fact that I'm thinking about equilibrium here. This correlation function behaves as a power law that looks like this. Next, I extended this definition to a time-dependent quantity. Yeah, here I'm talking about critical quenches to well, at a critical point, so T equals to Tc here. And here I'm thinking about the quench, where I will start from a disordered initial condition and I quench at Tc. Later I will discuss the case where I quench below Tc and compare with what I find here. So I said yesterday that this object has a separation of timescales, although I didn't call it this way, but now I want to introduce the notion or the concept, the name, such that it behaves as a product of two factors, one being the one above, and another one, let me see which is the notation that I used in my notes, another one that I'm going to call with a G. So what I have here is a scaling function that I'm calling ST for space-time, because it's a correlation that depends on distances in space and time. Time is measured after the quench, so if I add here an axis that describes time, I call 0 the initial instant where I'm quenching the sample and where temperature is set to be equal to Tc, and time is measured from here. So I don't know, this is a generic time after this initial quench. And this is the time that I'm using here to correlate on the same snapshot at the same instant the configuration of the spin on one side and on another side at distance r. So, what do you have to observe here? You have to observe here that there is a product. Let me show it with a cross and encircle the cross. And there is a product between a function, which is the equilibrium behavior of the problem at the critical point, times another function, which is definitely out of equilibrium. It depends on time. Okay? This is the out of equilibrium factor, if you wish. Why do I call it out of equilibrium? Well, because in equilibrium, equal time correlation functions should approach a constant. And this doesn't, because there is time still here. I said that this form is observed experimentally, has been observed first experimentally and numerically. It was next obtained with RG methods, extended to time-dependent objects. I'm not going to discuss them in much detail. What you can do in both cases is extract the functional form of this length, this growing length, RC of t, and find that it goes like power law with an exponent, which is what is called the dynamic critical exponent, and is the same value that you would find if you start your dynamics from equilibrium at the critical point. So you do, if you're used to I don't know, numerics, you do your Swensen-1-like algorithm to equilibrate your sample at the critical point. You have a configuration which is typical of equilibrium at the critical point, and you let it evolve in time. Then you can compute this kind of correlation functions as well and see how they behave. And you will find that they behave with an exponent and it's like that. Yes? Say it again. If there is any... No, it's what it happens. If you wish, it could be taken as a surprise. But in all the problems that we know, you can scale these things with one length. It's not completely true what I'm saying. If you have other parameters which are vectorial order parameters, and you have interactions which are, you know, kind of special that may couple differently, different directions of vectors, then you may have two lengths, say one associated to ordering in a plane, let's say, and one on the another direction. So you can cook up models for which you can have more than one. But okay, you understand why this is so, because you have different orderings in different directions. So yes, so exactly. So the RC here, what it's telling you is telling you something about the length of the patches that equilibrate up to time t. So if you go farther away from this length, then your patches are not equilibrated. So roughly speaking, it's not completely correct what I'm saying, but roughly speaking, what you can think about, imagine that you have a kind of a checkerboard configuration. So you have boxes of length RC of t, which are equilibrated, but then when you go and look beyond, this next box is not equilibrated with the previous one, and so on and so forth. See? Yes. No, it's power laws. Typically, it's power laws, and it's you can extract those power laws with RG's arguments. Well, the scale is RC. So if you would, let me say what this thing is doing. So it's going from a constant to 0, right? And going to 0 with some power law relaxation. So I don't know, x to the minus, let me call it, what should I call it? Z, or something like this. It can be very complicated, this function. I will show an example, the ON problem next, where it is not a power law. It's an exponential times a power law. Can take different forms. It's very difficult to give its full form. I mean, you cannot give its full form analytically, but somehow you can extract asymptotic behaviors. And you see that this length is the one that controls whether this argument of the scaling function is much smaller than 1, let's say. When it's much smaller than 1, this goes to the constant I was talking about over there, and you recover the equilibrium relaxation. While if you go to distances which are beyond this RC, then this is not a constant. It's important, and then it's the thing that will allow you to scale the data, as I said yesterday. Okay, so you can play the same sort of game with the two-time correlation function that I also discussed yesterday, or at least introduced briefly yesterday. So you see here I'm only using the symbol that represents the average over the noise. I could have not included it if the sample is sufficiently big, as I said. I could have also included the average over the initial conditions. They will all give me the same. This kind of self-averageness in this sense, in these problems, dynamic self-averageness. So this quantity also separates into two factors. And I'm going to call this one G2 time RC of t or RC of t weighting. So this stands for 2 times. RC is the same as the one that it's over here. And this also has a power law decay, and this has a behavior that goes from this constant also to 0. Oh, sorry. And these two zeros when x goes to infinity, as also here. Yes?
So, probably you have like one form of, but there is a constant bound to the extension. Why? Because it's down. Because if R is bigger than then sort of part of the system that's correlated.
Yeah, but I mean, there is this causality argument. I can also use it here. You know, I mean, because what the spins do in one end of their sample and what they do on the other end of the sample, they haven't communicated.
Yeah, but that's
beyond this
right,
R of t.
Right, but that means that if they, I don't know, if they're correlated to the beginning,
They are not, because my initial condition is disordered. It's fully disordered.
oh, so this is equilibrium for initial.
This is true equilibrium, the prefactor here. But whatever is beyond this line, if you wish, this is for the quench. So here it starts the quench. 1 little r is much bigger than RC of time. Then you see what's the initial configuration. Then you have information about your initial configuration, but not about the dynamics. See what I mean? If imagine that this is your sample. Okay? So take 2 ends of the sample. So these 2 ends of the sample, for times which are, so if the distance between these 2 ends of the sample is much larger than this RC of t, these two don't know of each other.
Yeah, but they can still be traced independently. Because suppose I start from relations that the relation functions decay quite slowly.
Mm-hmm.
It went to resistance, the relation functions decay fast. They can start decay independently. So
But then I don't understand what you say. You're doing the opposite quench, I think. Because,
you start always from
yeah, I could do it in the opposite way. I can tell you what happens if I do it in the opposite way. But I always, in this discussion, think about quenching from the disordered phase into somewhere. No.
But you don't see how power law but if my initial correlation is very, very fast
Okay. Okay. Well, there's another tricky issue there. The tricky issue is that I'm thinking about these spin systems. And these spin systems, for instance, in 2 dimensions, the completely disordered paramagnetic configuration, it's very closed, and even for certain lattices is critical percolation. So there are correlations in the initial condition that are hidden. So these are the ones that you may recover here in the behavior of this function. Okay? But if you really have initial conditions that are completely uncorrelated, as you say, then what you're saying is true. Okay. Okay, this is a, yeah. Yes. Yes. No, in these cases, it could be critical disorder, but in these cases, it's just a paramagnet. Okay? So it's a paramagnet, and here, it's a paramagnet. But for spin systems, you can have, even in a paramagnet, for certain lattices, some hidden correlations that you wouldn't imagine they are there. I'm quenching to TC. Exactly. Okay, so this is the recap of what happens when I quench at TC. There is a separation of timescales which appears as a product. Okay, it's a product, and I want to stress the fact that I have a product of two factors. One that tells me about equilibrium behavior, and another one that tells me about out of equilibrium behavior. And basically what I can think about is that at a given time t, I have patches of length RC of t, which are equilibrated. And then if I go and look beyond, I have like a superposition of these patches. I mean, wherever I sit, I can see a patch. Of course, these patches are fractal. This is just a sketch. Don't take it very seriously, but maybe it's good to think about this problem as having all this, patchwork of regions which are equilibrated. And if you go and look beyond, they are not at longer distances. And this is why you see the other factor appearing that takes into account this other behavior. Okay, now what happens if you do the quench below the critical point? So you do like this. You come here and you go to a temperature which is below TC and do the evolution there. So there you also have a separation of timescales, but it's additive. Let me put it here. So if I write this quantity, I will find, let me use this notation. So I have a sum of two terms in both cases, for both correlation functions and for any other one that you could like to define, where you have a piece which tells you about equilibrium within domains, and now the domains, I can see them clearly in my pictures, and what happens next. And again, I can, for these pieces, it's just the values that you know from equilibrium at temperature, which is far, typically, from the critical point, so they're not very interesting. Typically, they are exponential relaxations and nothing very, very interesting. But what is interesting is which are the asymptotic values of each of these pieces and how we match them. So let me discuss first the second case. So the second case, what am I going to do? I'm going to say that this quantity here is going to vary from 1 minus mx squared. This is equilibrium magnetization at the temperature at which I'm working. So let me call it this way. And this is at times which are equal. And it goes to 0 at times which are very far away. And the other one, I'm going to scale it in this way. Let's call it F. There I call it R. So 2 times R of t over R of t weighting with a function that goes from mx squared at t equals, or let's say t tending to t weighting plus, to 0 at times which are very far away. So what I'm doing here is looking at the two-time correlation function, so I'm comparing the configuration of the sample at two different times after the quench. And the separation that I observe in my data, if I plot this full correlation function, is something that looks like this. So I'm plotting curves for different values of the weighting. I see non-stationary relaxation below the plateau. And how do I interpret these curves? Well, I interpret them in this way, with this additive separation of two terms. One of them, I'm going to draw it with the dashed line here. I'll try to be more or less in agreement. So this is the translation of this little thing that goes to the plateau. Plus, so this is what I call Cx of t minus tw here. And then I have another piece which is equal to this. And this is the other contribution, which is what I call Ch of t comma tw. Okay, so the observation that I have is that the full correlation function behaves like this. It approaches a plateau, and then it decays from the plateau. The way in which it approaches the plateau doesn't depend on t weighting, because all these curves fall on top of each other here. So the relaxation is stationary, in the sense that the times enter through the difference between the two of them only, and not depend on each of them separately. But then when the relaxation goes below the plateau, I see the waiting time dependence. I see the dependence on the two times separately. And it's convenient to normalize these two contributions in such a way that one goes from 1 minus mx to 0, and the other one starts from mx. Here, I should have, sorry. Let me say here. So this is the CH. And the other one starts from mx and then goes to 0 in such a way that the sum of these two gives you the bow line. Yeah. Exactly. Yes. So I'll come to these figures in a second. So here we understand perfectly well what's going on. Let me show you some pictures to discuss this with the pictures, and maybe we'll be. Remember these pictures that I showed you yesterday? So this is the disordered initial condition. This is intermediate time. This is later time after the quench. So you see here in these pictures that you have these domains, right? In this special picture, for instance, if you look at this domain, you will see that there is a fluctuation here. In this one, there are some fluctuations over there. There are some spins which are reversed. Here there is one within the patches which are ordered in either red or white configurations. So these fluctuations are thermal fluctuations within the ordered structures that you would have equally well in a fully ordered configuration of equilibrium. So remember that I showed you some equilibrium configurations where the sample was at a temperature which is smaller than Tc, ordered, and there were some reverse spins due to thermal fluctuations. So here you also have the thermal fluctuations. They're not very visible in this picture, but they are over there. And if you forget about the fact that your sample is a mixture of the two up and down configurations ordered in these domains, if you forget the existence of the domain walls, for what is within the red configurations and the white configurations, you have the same thing as what you have here. So these fluctuations that are due to temperature are very fast, as I already said yesterday. So if you compare equilibrium configurations at different times, you will see some decorrelation due to these fluctuations. And this decorrelation can go from 1 at exactly equal times, when you just correlate your sample with yourself, to some value which is mx squared. It cannot go farther away than mx squared. Because in my Ginzburg-Landau picture of yesterday, if I'm in equilibrium, the sample is here. If I think about this point as a particle in a potential, this particle is coupled to a bath, so it's doing some kind of random motion. The farther away it can go is the size of this well. And the size of this well has to do with the fluctuations, due to these thermal fluctuations. I mean, the thermal fluctuations allow the particle to visit the well, move around, not stay in the minimum, because it can move. And if you think in terms, if you associate the size of this well to how far away this particle can go, and so on and so forth, what you will find is that here it cannot go beyond mx squared. In other terms, still, if you remember statistical physics in equilibrium, and you have a correlation function like this that you want to compute, what this can do, well, at very long distances, or equivalently in these terms, at very long times. So I'm looking at equal point correlation functions different times. So let's write it here. What this thing will do is that they will decouple. If I'm in equilibrium, these two factors are equal to mx, and the two factors give me mx squared. So this justifies the fact that this correlation at the beginning, where I only see the fluctuations within the domains due to temperature, decorrelates from 1 to mx squared. Next, what happens? What happens is that there are walls, there are interfaces, and these interfaces are not fixed, because as I said, there is elastic energy or surface tension or interface energy that the system wants to get rid of, and the way in which it gets rid of is by growing domains. And by growing the domains, the walls move. This situation is not static. It's not only thermal fluctuations within the domains that you have, you also have the motion of the walls, and the motion of the walls is the thing that gives you this decorrelation, because this configuration looks very different from this one. If I do the correlation between this one and that one, certainly I will get a value which is lower than mx squared, because the walls moved. And this is the reason why this thing goes below mx squared to 0 eventually at very, very long time difference. Now, the way in which the walls move, one can associate in different ways. I'm not going to do it, but we can argue how the velocity of these walls depends on time. And what you can see is that the velocity of the walls depends on time in a way that decreases when time increases, so they become slower, these walls. And this is, in the end, the reason why these curves decay in a slower manner when the waiting times are longer. So I didn't say how these times are ordered. They're ordered in such a way that TW1 is smaller than TW2 and is smaller than TW3, and so on and so forth. So older samples, in the sense of TWs longer, decorrelate in a slower manner. And why do I say so? Well, just to stress it a bit more, I say it because if I want to see at what time difference the sample reaches at certain value, say 0.5, of the correlation function, well, it needs this time difference for this waiting time, for TW1. It needs T minus TW1, say, to 1. But it needs a longer time for this waiting time. It needs this from here to there, time delay, and so on and so forth. So that the correlation is slower when the waiting times increase. And this is exactly the same aging phenomenon that Jorge must have talked about last week. Only that here we understand perfectly well what the sample is doing. We have a microscopic understanding of, what the sample is trying to do. It's trying to order ferromagnetically, but as I said, it orders ferromagnetically in the two equivalent configurations in different places. Naturally, there are these walls there, and these walls tend to disappear in time, but they tend to disappear ever more slowly as time goes on. So all this mechanism will go on forever if your sample is infinite in size. Why? Because again, the size of these domains is characterized or is quantified by this R of t. There is also an R of t below the critical point that here I can see even more visually than before. It is the typical size, linear size of these domains. And if I want a domain to cover my sample, I need R of t to become of the order of L, the linear size of the sample. But it turns out that this R of t below the critical point, it typically grows also as a power law, but with a different value, with a different exponent from the one that I discussed before at the critical point. But it's still a power law. There are other cases that I will discuss later, but typically it's a power law. And okay, if you need this power law to reach L, as yesterday, T has to diverge with L. And if L is taken to infinity at the beginning of the calculation, so the thermodynamic limit is taken first, and long times are taken eventually later, but not scaled with L, then you will never reach L with R of t. So again, you can extract from here an equilibration time that will go like L to the ZD for temperatures below Tc. Okay? Yes?
Just want to think about this as kinetic. One short one and one moment short one. And so that will sort of give moments of time and sort of distribution with respect to both tendency and temperature and this R. But this R is slow.
Well,
If I can probably write some conjugate to this R to get this force equilibrium with this type of domain, and probably I will refer to
I'm not that sure. I mean, because let me see. So what you want to do, but then you want to do a static calculation.
yeah, static calculation, but I somehow impose some staggered field or whatever, staggered random field which gives me equilibrium value of this R.
But what is the equilibrium value of this capital R?
Well, I just enforce a staggered field. Then I would use
Well, I'm not that sure. But anyway. You can do certain mean fields that allow you to, I'm going to do one next, a large n mean field that allows you to compute all these things, but of course it doesn't give you the results for finite dimensions as usual. But it doesn't work in this way. I'm not that sure that one can do a calculation like the one that you propose. But okay, we can discuss it later. But I don't see very well how it could work. Okay, so yes, please.
So thinking about the latent
Yes.
So you showed us like the three energy density
Yes.
plan, but thinking about three energy plan states, I guess is a function of the whole configuration of all the
Yes.
is it, you know what that looks like?
No, this is something that I tried to say yesterday, is that this picture for certain aspects is useful, like what I said before, but for other ones it's very misleading. Because, exactly, as you say, here I'm only writing phi, but then there are all the other components of the spins, which I'm not taking into account within this average over the full sample. So, no, I mean, it's very difficult to go and have a look at everything which is going on in these transverse directions, right? Yeah. Yeah. This is again misleading. Yes. So I don't know how far Jorge went last week, but in many of the models, mean field still models of glasses that we understand very well because we can solve them, in many ways. There, what happens is that aging is due to moving on a flat landscape. So it would be in this picture something like imagining this maximum here reproduces in the transverse direction in a parallel way. So imagine that you have the same thing reproduced in this transverse direction to the blackboard. So you have like the two wells that are like this, like two channels, and then you have a barrier in between. But then you can move pretty easily along this maximum that has n-1 directions in which it's flat. So it's a bit like this. The question that you asked, the answer in this problem is a little bit like this, but what I cannot quantify here is exactly all the small barriers, the ones which are subleading and then the number of spins in the sample. So basically, as here and in these glassy models, the aging dynamics is not due to jumping over barriers, which would be the image that you would get from doing something like this in this problem, which has nothing to do with the dynamics I'm showing here, but it's more like moving along this flat line over there. So it's a bit like a random walk along this line, which is actually not only a line, it's an n-1 dimensional space, so it's huge. So your random walk, has a lot of space to move around. And glasses is like this. You have something that we call the threshold, which is like a flat region in free energy landscape, which is not exactly flat, has some structure, but it's mostly flat. And then you can understand this aging dynamics in glassy systems thinking in those terms. But it's certainly not jumping over high barriers. Yes. 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 Yeah, so what I'm doing here is I'm doing a double limit. So I have two times. Your question is good because it allows me to make precise what I didn't make sufficiently precise on the blackboard. So you see, I have to think about this curve as a function of two variables, but I'm plotting it on the blackboard as a function of only one variable, t minus tw. So this part here corresponds to a limit, the approach to the plateau, corresponds to a limit in which I'm taken, I write it down here, the limit of t minus tw going to infinity, the plateau, the separation of timescales like this, but t minus tw much smaller than tw. So you see what I mean? First of all, I take tw to infinity. And next, I take t minus tw to infinity. So I should have written it in the opposite order. Let me write it like that. T minus tw infinity. So this is the first limit I take, and this is the second limit I take. So time differences. Okay. Time differences are much smaller than the waiting time in my procedure. So concretely, in a simulation, what do? I take the waiting time to be 1,000,000 Monte Carlo steps. And then I take the extra time to be 1,100,000 Monte Carlo steps. So then, t minus tw is large with respect to that this thing very, very large, so 10 to the 6 Monte Carlo steps. But t is close to it. So t is 10 to the 6 plus 10 to the 5 Monte Carlo steps. So this is the limit in which I'm approaching the plateau. Next, I go beyond this limit, and if I still let t grow, say when I go to twice 10 to the 6 Monte Carlo steps for t, then I'm in this region over there. Why is it so? Because I say that the scaling variable of the part term that describes this decay is the ratio between the two times. Sorry, the lengths evaluated at the two times. I said that the lengths go like, oh no, I think this is the thing. So if I take t to be twice the waiting time, then I have something that deviates considerably from 1 here. So it's 2 to 1 over ZD. So then I enter the regime in which the correlation decays below the plateau. If instead I took t to be 10 to the 6 plus 10 to the 5 with respect to tw, then the 10 to the 5 I drop, and then this scaling argument is 1, and then the second part, the second term is just fixed, it's a constant, it's m squared, and then I get the plateau. So this is the way in which you have to think about the two regimes. It's yeah. Yes. But if they are separated by very long times as well. In this example of the particle in a well, imagine that you take a particle in a harmonic potential and you couple it to a bath. So then if you compute x, the position of the particle, of t and x of tw, average over the noise, and you take t to be much longer than tw, then you can factorize these two. And then you will get this value here, let me call it, I don't know, x0 squared. So I'm using exactly the same argument here. Sorry, TW set by? No, TW is a parameter. You're an experimentalist, and then you can choose TW to be 1 second after the quench, 10 seconds after the quench, 100 seconds. It's just a parameter that you have at hand that you can choose as an experimentalist. Yeah. Okay, so let me recall something that certainly Jorge showed yesterday, or last week, which is let me see, this kind of curves. I'm sure he must have shown this sort of curves. So these kind of curves are correlation functions in a Lennard-Jones mixture. So these are particles in interaction in a box, and that's the relevant correlation function that you can compute, which is basically density-density correlation function. And they are presented in Fourier space, so you are considering the correlation between 2 points at distance r at different times, tw and t, and you Fourier transform with respect to distance. So the q, which is over there, is wave vector with which you do the Fourier transform. But once you fix q is fixed, and then you don't move q in this plot. So it's exactly the same kind of plots that I showed here, but for a different system, where you cannot identify domains. We don't know how to do it. Maybe they are, but we don't see these domains. We don't know how to see the other regions separated by domain walls. Still, the shape of these correlation functions are very similar to the ones that I showed you here, even with the plateau. Well, maybe it's not so neat, the plateau, as it is in this sketch, but it tends to be, one can think that it's there. And the dependence on t-weighting is the same, so t-weightings increase towards the right part of it. And so qualitatively, you have something very, very similar. Only that you cannot get a visual interpretation of what's going on. And if you look at the space-time correlation functions at equal times, different positions in space, and then you don't see much going on either. You cannot identify an R of t. So we don't fully understand what's going on. There are certain tricks to identify or try to think about some distances that grow in glassy systems, but I'm not going to discuss them. Are a little bit technical for my purposes here. But I just wanted to highlight this kind of plot to tell you that there are connections between what we see here and what we see in glasses, although we don't understand them in full detail. And this is just something to recap what I've said. So this is the kind of the behavior that you should see in a quench to the critical point, with plots with different colors corresponding to different waiting times, and this multiplicative separation of timescales at the critical point is seen as this kind of the fact that there is no plateau at a finite value of the correlation function, but instead there is kind of an envelope that goes to 0, and this is not shouldn't be surprising at this point, because at the critical point the order parameter is 0. So there cannot be a plateau at a finite value of the correlation function with these arguments that I was using. So the equilibrium part of the relaxation at the critical point should go to 0. It cannot go to a finite value. So the fact that it goes to 0 is represented by the fact that there is this envelope that I'm here showing with a dotted line that goes to 0, which is the relaxation of the equilibrium part. And then there is the waiting time dependence here that in this sense is relatively similar qualitatively to the one that we have over there, although the scaling functions are different and the growing length is different as well. But grosso modo, what's going on with the color lines below the envelope or below the plateau is roughly the same. Okay. So the same thing can be done for space-time correlation functions, but it doesn't add much, so I'm not going to show them here. Okay, so this is what I wanted to tell you from a kind of phenomenological point of view. I haven't proven anything of what I said. I just showed you pictures and functions on the blackboard. So what I want to do next is to do a calculation and argue that at least in mean field models, in one mean field model, there are other ones that one can treat as well, but in some cases, one can cook up a model that one can solve until the end and find that this phenomenology is realized. And this is the ON model with n going to infinity. So let me in half an hour give you the basics about the ON model. Yes. Yeah, it's a little bit what I'm going to do next. It's kind of, it's not a hydrodynamic limit, but it's the time-dependent Ginzburg-Landau version of the problem. So it's introducing a continuous order parameter and trying to write down an evolution equation for that.
Okay.
Yeah. Introducing a time-dependent version of the Ginzburg-Landau approach. So Ginzburg-Landau, as I said yesterday, what do? They define an order parameter. In what I said over there, I was thinking about the global order parameter, where I sum over the spins in the full volume V, so V is the volume. And I go then from Ising variables to a continuous field, a continuous variable at this stage. with phi taking values in -1 and 1. And so it's continuous. Now, next thing they do is to say, well, let's think about a local order parameter. And instead of summing over the full volume, let's sum over a volume, which I'm going to call V, centered at some point R. Yes, R is the lattice side. Yes. It's a label that tells you which is the site on the lattice. And then you construct in this way a function which is still taking values in -1. And 1, it's still continuous, but it has some local information. So what they do next is to define a free energy functional, which will depend on certain parameters. I will write them down next. I think this is the notation I'm using. So the notation I used yesterday. So you have a functional here which has this term that tells you how much it costs to have a wall, as I said. So this is a gradient in space acting on the field. And then you have a kind of potential energy, which is this free energy landscape that I was drawing already yesterday in this form for the situation in which in equilibrium you are below the critical point, you have this double well structure. So you have two minima here, and the functional form I will choose for F is this one. Okay, it's a double well. I have two parameters, G and lambda, and these are the two parameters that I'm going to write here, and there's an elastic constant that I could have included here, but I can divide it away by redefining the field, so I don't write it. So I'm left with two parameters, G and lambda. Okay, so this is where Ginzburg Landau start their analysis, if you wish, of static properties. Next, what we want to do is dynamics, right? So we want to propose some dynamic evolution to the variables, the spins, but this is difficult because they are Ising objects, so it's not easy to work with Ising objects. It's better to do it for the field, because the field is a continuous variable. So, proposal. Sorry? The V is some volume around the spin. It doesn't have to be very small. It has to have, well, I'm not going to discuss the scaling of this V of R, but it's, like a bubble that you construct around your site to do the coarse graining of the spins and actually get a continuous variable that varies continuously in this interval here. Because if you take VR to be very small, you sum over 4 spins, you don't get a continuous variable. So VR has to scale to infinity somehow, but it has to be much smaller than the full volume of the sample. So, okay, there's a tricky business there that I don't want to discuss in detail, but it can be done precisely. So, proposal, the field phi of R becomes a phi of R of t, time now, as well. And the evolution is given by a Langevin-like equation. Acting on this function, phi. So the Langevin equation, I'm going to write it in this way. To write it like this. So I dropped the inertia-like term, acceleration. I'm assuming that I'm in an overdamped limit. This can be checked a posteriori, that is good enough for this problem. So I don't have to keep the acceleration term, which is nasty to do calculations. But in the end, you get the same thing. So, you have to do the analysis of the timescales and so on. Timescales associated to that term are too short, so you can drop. So this is the dissipative term. This has to do with friction. There could be a friction coefficient here, but I'm going to send it to 1 through a redefinition of time. This is standard. There is a deterministic force that is obtained from the variation of this free energy light functional that I have defined here. And there is noise. And noise, I'm going to take it Gaussian distributed and white, though it will be convenient at a certain point of my calculation to introduce a finite timescale into the correlations of this noise, so it's going to be slightly colored at a certain point, and this is just to avoid some divergences that otherwise you would have at very short times. Well, it's a little technical issue, it doesn't matter so much. The point is that the noise will have zero min and will have correlations that I'm going to write in this way. Like this. And it might be useful, actually not in time, it might be useful to regularize this delta. It will be useful to regularize it later, but I will tell you where it appears and don't bother right now here. So, sorry, this is slightly colored. What I mean is that this one will have a short distance cutoff that one can associate with this lattice spacing. Anyway, I mean, there are different ways to do it. It's not very important at this point. But I'll keep it white. I made a mistake when I said it was slightly colored. I'm not going to do it. So, okay, this is my starting point. Now, if I write down explicitly what this deterministic force is, I take the variations and I will get this thing here. So I will get plus 5 degree T minus lambda T plus psi over RT. Okay, so the variation of this elastic term will give me the first term here. This is coming from F, and the other one as well, the second one as well. So this is almost a linear equation, but it's not a linear equation because of the phi cube term, which is here. Yes? Here? Yes, it's the gamma here. I guess that this is what you're thinking about. If I put a gamma here, I will have a gamma here. But usually one redefines time, it's the gamma in the definition of time, and then it disappears from here and from here. So let's stress that it's almost linear on phi. Of course, it's not linear, and this is all the complications. This brings all the complications to the problem. But what can we do with this term? So there are different ways to try to linearize this term, keeping the important piece of information that we need to recover the results that we want to have. So one way to do that is to go to this ON model. This N here is not, I will try to write it differently, it's not the number of spins in the sample, it's another parameter. And what this ON model means is that instead of working with a scalar field, phi, over p, I'm going to upgrade the scalar field to a vector field. And this vector field will have n components. Okay, so it will have n components. So in a sense, I have two dimensions playing in this problem. I have the dimensions of real space, which is D, so R has x1, xd components. So this is the dimension of real space. But then I have this kind of internal dimension, n, that I introduced by hand. Now what I want to do is to upgrade f to be a function of this field, vector field. So here I can just simply say, well, I'm going to put an arrow. And now I'm going to explain what this notation means, because this square now is a scalar product with respect to the real space dimension, or the real space, and a scalar product with respect to this internal space as well. So basically here, since I don't have a lot of time, what you will have to consider is the derivative with respect to all the coordinates in real space of each of the components of this field, and sum them all. So what I mean here is that you will have terms of the kind d phi 1 x1, d phi 1 x1 plus d phi 2 x1, d phi 2 x1 plus d phi n x1 d phi n x1 plus d phi 1 x2 d phi 1 x2 and so on and so forth. Okay, you have them all there in this double scalar product. So this is a term that it's order possibly n times the dimensions of space. Now what do I do with the local free energy contribution, this f of phi? Well, this f of phi, let me do it here. Naturally, I will want to upgrade it to some f of vector phi. Now, the f of phi had a piece which was g squared, and another one which was phi fourth. And if I think about having upgraded the field to be now a vector, this phi squared will become something like the sum over the components from 1 to n of phi alpha squared. So it's something that I can imagine it will be order n. There are n terms in this sum, n positive terms in this sum. So here, the second one will be, if I do it like this, if I keep it like this, will be order n squared. If I look at this, it will be so if at some point of my calculation I would like to take a large n limit, this term written like this is much larger than the other one. If I would like to take n to infinity, this one is much larger than this one. This is completely negligible with respect to that one. And I don't want that, because I want to keep the structure of this kind of double well with height here, which is basically controlled by the phi squared term. So if the phi squared becomes negligible, I won't have this bump. So to cure this problem, and this is quite standard, what one does is to scale this term with n. Okay, to add a 1 over n here in such a way that you will recover the good scaling for both. You get rid of one of the n's here, and then both of them are of the same order. But apart from that, I have the same kind of potential. Apart from this 1 over n here, is the same form of the potential that I had before. I'm calling potential this part. So now I have a problem that is well defined, it seems, and I may want to study its statics and its dynamics. First of all, I want to know if there is a phase transition, because I want to have a problem with the phase transition, especially with the second order phase transition, as the ones that I discussed. So I can compute the partition function as a function of inverse temperature and the two parameters in the problem. Since I have 10 minutes, I will do the summary of the static results, and I will introduce the Langevin equation, but I leave for tomorrow the dynamic part, because otherwise I won't have time to do it. So what happens with the statics? I'm not going to do all the calculations, but here comes the convenience of having introduced this 1 over n here, and that I'm going to use to decouple this term. Why so? Because at the level of computing the partition function, what do we have to do? I have to sum over all the components of the field. I'm using this symbol to say that this is the partition sum, or this is the sum. And then I have to do the exponential of minus beta, this big F of phi. So f of phi is almost a squared. It's almost quadratic, apart from this one, as the Langevin equation was almost linear apart from that one. So what I'm going to do now is a decoupling of the 5/4 lambda 5/4 or 4 term. So this goes like this. I have an m here. So this term is the same as lambda over 4 phi squared times phi squared over n. Now phi squared over n, if I add an n here, okay, let me write it down again. There is a sum of many terms, if n is going to be taken to be big, normalized by 1 over n. So this quantity I can imagine that is not going to fluctuate much if n goes to infinity. If n goes to infinity at a certain point, can imagine that this quantity will not fluctuate much. Let's put it between inverted commas like this. So the idea is to say that instead of working with this fluctuating quantity in the partition sum, I'm going to replace it by its average. It's equilibrium average, because I'm doing equilibrium here. In other words, this is the thing that I'm going to use. So the phi squared over n here, I'm going to replace it by its average. It's a proposition. The proposition is then to make this f quadratic in this way, because one is fixed to the average that I don't know yet is fixed with respect to the partition sum. Then with this, the sum to perform is Gaussian. I know how to do Gaussian integrals. So if I do the sum with the Gaussian, I can find a self-consistent equation for this average. Because within the Gaussian, I can compute this average. I can compute phi squared x within the Gaussian sum, and find a self-consistent equation for this phi squared x. Okay? So if you do that, I'm not going to detail this, it's just Gaussian integrals. What you will find is an equation that looks like this, and I will define this in a second. So we have this. So if you do these calculations until the end, what you will find is, just look at this equation. You will find an equation, the first and the last part. So you will find a self-consistent equation for the correlation length in equilibrium. Okay? Where the volume of the sample appears, this is a sum over wave vectors. This is temperature at which you are working, and this is the lambda and g are the two parameters in the problem. This is doing the large and limit. This is, you get, when you do this large, you use the large and limit, the only place where you use it is to say, in the large and limit, this factorization I can do. This kind of replacement of the fluctuating value by the non-fluctuating value, by the average value. Is there that you use the assumption of large n? Yes. You can also do it this way. It's also the Hartree approximation for those applied to the scalar field is what in field theory people usually call, or in condensed matter, Hartree approximation, which is only an approximation for a scalar field and can be pretty bad in certain cases. But for the large n, it's exact. For the large n, you can do all the diagrams, as you say, and you see that the other ones don't contribute. Yes, I think so, if I'm not mistaken. Yes. Also. Yes, also. Yes. That you can do it in different ways. This is what people I think that this is what people in field theory call the gap equation. This is the mass of your field. All these things appear in this equal to this is what sometimes in field theory is called the gap equation. And this, the mass of the field is psi x minus 2, right? Yeah. Sorry? Yeah, psi is the equilibrium correlation length. Sorry, say it again. Yes. This is why exactly. This is why I'm using an ek under the psi, not to confuse. Yes, I realized after I wrote my notes that I was using the same thing for the noise and for the crack. Here. Exactly. Yes. So this sum, psi to the minus 2. Yes. Sorry for that. Yes. So, but there is also a problem with the sum. Yes. I'm not sure I understand your question. I mean, yes. Yes. Actually, well, you can do that as well. But at this level, the only thing you need to know is how this psi x behaves as a function of temperature. And what you will see, I only want to pinpoint for the moment the existence of a transition in this problem. And I just want to say to what this transition corresponds. I mean, how can I interpret the transition? With this formalism, you can compute 2-point correlation functions as well. Once you have Gaussianized your exponential, then you can compute everything. Okay. Gaussianized. Neologism. No, but I don't have Gaussian modes here. No. This is it's simpler than that. I mean, just so I mean, what I want to say is that this sum is tricky. Why is it tricky? Because if psi is finite, there's no problem. No, there is no divergence here, and everything is fine. You can do the sum over the K modes. Go ahead, take the infinite volume limit. Everything is fine, and there's no problem in that sense. And this happens above a critical temperature. So above a critical temperature, you will find a solution to this equation such that psi x is finite. And this is the disordered usual phase, no problem with that. But it turns out that there is a temperature at which you no longer find a solution with psi x finite. Psi x will diverge. When psi x diverges, this regulator, this mass, disappears. And then you have 1 over k squared here. So you have to be careful with the sum, because it will diverge for small values of k. So if you treat the k0 mode separately in this sum, so you separate it from the sum, and you put it, as a only term, and then you sum over k is larger than 0, something that you can do because I'm implicitly working at finite volume here, so I have a gap between the k's, the 0 and the other ones. So then you can treat this sum carefully. I'm not going to do it. It's just standard things. You can find it in Baxter's book, for instance, or in different papers. The fact is that the behavior of the xi changes at this critical temperature, and xi becomes something that I've written down somewhere. Here it is. At the critical point, psi x is a function of temperature difference from temperature distance from the critical point, as usual, but it's also a function of volume. So exactly at the critical temperature, I don't have any more the divergence. I have divided it away, if you wish. I only write down here the divergence with the volume. I have a divergence with the volume. And below the critical point, psi x goes like something that also diverges with the volume. So there's a square here, T minus Tc over Tc. There is a phi 0 squared here that we'll define next, and V. So here the divergence occurs with an exponent that is a function of dimensionality. I could write it down, it doesn't matter. So lambda bar, let's call it, not to confuse with the other one. It's not this one, it's an exponent. And here it diverges with 1, only that I wrote psi square over there. So if you look a little bit at how the average of the field of the phi behaves, what you will see, any of the components, say you pinpoint one component, and then you see how it behaves, this field. What this field will do is that it will condensate. It's a bit like a Bose-Einstein condensation phenomenon, in the sense that the field will take we have a zero wave vector component that is a function of the volume, that diverges with the volume. And the other wave vectors are finite, okay, with respect to the volume. So the field tends to condensate on this zero wave vector, and if you compute the correlation functions of the field at wave vector k, so if you compute C, running out of Blackboard, if you compute Cx defined as this, you will see that this object behaves very differently for k equals 0 and for k different from 0. Basically, it's a function of the volume here, and it's not a function, it's finite there. What do I want to stress about this? I want to stress the existence of a critical temperature. I could give you the formula that determines it, but it doesn't matter so much. There is a critical temperature, and there is this zero mode peculiar behavior appearing. So this is a recap of the statics of this problem. Now what we want to do is to do the dynamics of it. But since I don't have any more time, I will leave it for the next lecture. The idea is to write down this equation for each component. So you will have a alpha, you have an alpha, you will have an alpha, you have an alpha, alpha, but here, what do you have? You have a phi alpha times phi squared that will appear. And you will do the same kind of decoupling here, only that now you have to be careful with the time dependence. And that we will do next time, but it can be done. The equation can be linearized and can be self-consistently solved in such a way that the value of this that we will replace by a mean will be fixed with a self-consistent equation, kind of this one, but it will be time within it, more complicated. But it can be solved as well, and then you can think about what happens with the dynamics at the critical point or below the critical point. So, okay, I will stop now because I went over 5 minutes, and can take questions if you wish or more discussion.